Before this video starts, I just want to emphasize that I am by no means stating that anything in this video is fact. I am simply a mathematical enthusiast who loves all things math related. I am obsessed with division by zero, and these are my findings. I hope this helps you to understand even a little by as to why these numbers are undefined and indeterminate, but also provide a bit of context for their usages in very limited scopes. This will be the first part of 2 or 3, depending on how far this, how much we can get out of this. So the first thing we're going to need, of course, is a symbol. And what perfect symbol? What more perfect symbol is there than a paper I found on this here? So on unicode.org, there's this nice paper from 2006 that illustrates a few interesting symbols, and one of them that I found seemed almost too perfect to be true. It's the lesser known symbol of the Latin letter reversed C with a dot. As you can see, it's got some interesting meanings which you can view in this paper, and it fits the purpose quite well as a backwards C with a dot in the center. And I think it's only perfect that we use this symbol to the fullest of its abilities. Now, upon further reading, I discovered that there is in fact a symbol that is a backwards letter C with a dot in the center, which just looks like a regular C with a dot in the center. So I think that is the symbol we will use. Voila. There it is. So we're going to need a few definitions to begin ourselves off with. And I think where better to start with than by defining, we're going to say that x over 0 is equal to this symbol subscript x. Now, why are we doing this? What we want is we want to quantify this expression as something. So we're going to make it equal to this symbol up at the top here. And we want to retain the property value, so I'm just going to put it in the subscript so that it can't really be affected the same way. Just know that each one of these can be replaced with the other at any given time. These are equivalent for all purposes. So with that out of the way, let's start. So x, we're going to define, can be an element of any real number. It can also be an element of any complex number. And we'll say, we'll stick with that for now. That seems like a pretty good definition for us. So with that out of the way, let's start. So first thing we're going to do is we're going to cover how addition works, and we're going to just use variables in a similar format to this expression here. So the best way to quantify this expression is to cover how it operates. So of course, a over b we'll cover. And will be plus minus. We'll get both out of the way right at the start. Plus minus c over d equals a times b, d plus b times c over top of b multiplied by d. And these are equivalent statements. Oop, there's a minus in there though. And so we're going to use this statement here to handle this statement here and treat them the same. So how are we going to do that? Very simple. I'm going to start with just in this position here. We'll then try the position on the other side and then in both sides. So here we go. X over 0 plus minus y over z. We'll just assume that all variables are the same thing as x for now, because we're going to be going through a lot of them, with the exception of probably e and pi and tau, if we ever decide to use tau. Who knows? Anyways, so this turns out to be x multiplied by z plus minus 0 times y over top of 0 times z. So this is cancelled. We'll cancel the z's. Why are we canceling the z's, you may ask? Well, very easy. Bed mass says brackets first, then exponents, then division, then multiplication, then addition, then subtraction. Not the other way around. I know some of you know of a similar one. It's called PEMDAS. This is wrong. Never use PEMDAS. Bed mass. You have to handle your fractions first. So divide, then multiply. And that gets us x over 0. There you go. Which in turn gets us cx. So we now know anything you multiply or subtract into x over 0 is and will always be x over 0. What now, what you ask? Well, we'll flip the tables. We'll change to y over z plus minus x over 0. My, how the tables have turned. So now we have a number, and we're going to be multiplying or subtracting the constant number into it. All right, so let's do that. We're going to say this is equal to y times 0 plus minus z times x over top of z times 0. All right, so this is fairly interesting. So this, of course, is stricken from the record, and as are these. But now we have the plus minus symbol, the x, and the 0. So we get plus minus x over 0. And the reason this works is addition, doesn't matter which side your operator is or your variable is on, you will get the same result. But for subtraction, if it's on the right, you will get a different result where it is negative. So we can write this as constant plus minus x. And now we have a property. So we know it is possible to change the x in the operator, which automatically starts to rule out some interesting things. We know now that there is a tangible value of x that can be adjusted even with the division having a 0 in it. So we can actually access the property here. There is a property that is accessible here. So now we need to see what are the limits of this property and how, to what degree can we access it. All right, so let's access it now. So here's what we're going to do. Now we need to get through our multiplication variables. Of course, this is very simple. We all know this. This is a over b times c over d is equivalent to a times a times c over top of b times d. Very, very simple. So with this, now we just need to plug into one side because both sides will be the same no matter what. X over 0 times y over z equals what? X times y over top of 0 times z. And this, in turn, equals x times y over 0. So this is already an interesting change because we've just adjusted the property to have two values. So now it's c x y. So it's acting pretty normal above, and now we've got these fairly interesting properties below. So we can multiply in a number, but it doesn't. It's interesting because it doesn't care about the denominator. It only cares about the top. So this base z, it doesn't care about. So let's do division now. So division gets a bit interesting, of course, because we have a over b divided by, yes, I'm going to use the division sign. When was the last time you saw this? Divided by c over d. So of course this is kind of like a cross multiply. So it's a times d over b times c. This is an interesting property for us to use. And of course, once again, we'll have to do the x over 0 on both sides. Once there, once there. So let's do it. We'll start with it on this side. So we'll go x over 0 divided by y over z, like so. And this will get us to x times z with y times 0 in the base. This equals to c x z. So now the base is retained, but the number in the top of the fraction is lost. So there is value below, and as we've shown before, there is a value in the just in the top. So multiplication retains the top of the number, and division retains the base. So you can imagine in a situation where you have a number like if we had like 1 or here 2 over 0 divided by 10, this would equal to 2 times 1 over 10 times 0, which would equal 2 over 0, because the 1 is retained, which in turn would equal C2. Alright, so now we'll do it on the other side with the alternative. So we'll do y over z divided by x over 0. So this is fairly simple. Y times 0 over top of x times z. Now it gets interesting. By having a number, this is the number we have, and then dividing a constant from this number, we can get a result that's not a constant. But what it is, watch this, it's 0 divided by x z, which equals 0. So this is interesting, but it only works in this case. There is a theoretical case where you can use a 0 divide to get a zeroed result. So this is very interesting, and we need to take note of this. We need to keep note of this. All right, so we've done our division, we've done our multiplication, and we've done our addition. But what we haven't done is in each variant of this scenario, we haven't done a 0 divide plus minus a 0 divide. We haven't done a 0 divide times a 0 divide, and a 0 divide divided by a 0 divide. So now we're going to do that, just to get that over with. Okay, so x over 0 plus minus y over 0. These can be the same number, or they can be different numbers. That's not what we care about. All right, so here's how it goes. It goes x 0 plus minus 0 for y over top of 0 times 0. And you'll note this is actually very interesting, because these both cancel, and now we have C0. So a constant by a constant, or constant C by constant C, will always be C0. So this means that they always tend towards this number, whatever this number is. Keep this in mind, because we'll see what this number is soon. Or rather, we'll define what this number is soon. Okay, so let's move on. We're going to go to multiplication. So we've got x over 0 times y over 0. So this is very simple. It is, as you may know, x y over 0, which equals c x y. So it's the same. It's the same, because as we know from our previous experiment here, it doesn't matter what you put in the base. This is ignored, and only the top is retained in the property. subscript. So now, of course, we're going to do the same thing with division. Okay, so x over 0 divided by y over 0 equals x times 0 over top of y times 0, which equals 0 divided by 0, which equals c 0. So we just got the same results as our addition and subtraction, though in remarkably a slightly different manner. So once again, it tends towards this. So multiplication is the outlier here, because addition and subtraction give you these results. Though there is an interesting thought to go beside this, because it should be noted that if I were to multiply 0 into this statement, we will not in turn get our x or y value back out. For example, I have x over 0, and I say this equals cx, and then I multiply. I multiply 0 over this. I will, unfortunately, I will get right back out. I will get c0. So all the numbers tend towards here because I put 0 in. We cross multiply. It doesn't matter what's in the base of the 0. It can be 1, it can be 0, it can be, it doesn't matter. We'll get this number, c0, back out. So this is a very important thing to note. So now we have the 0 components of each when they interact with each other. And in this situation, we always get a situation where we get this number. Because you have to remember, we start with a division. So it would make sense that there's an oddity up here because we're starting with a division anyway. So there's always a divisive property. Oh boy, but we haven't even scratched the surface yet. It gets weirder. It gets weirder still. So we haven't covered exponents yet. The E in BEDMAS, so to speak. So let's do that now. Just gonna, yeah, well, we can use the remainder of this page here. So we're gonna say x over 0 is going to be raised to the property of, to the value, I should say, of y, like so. And then this is equivalent to saying x to the y over 0 to the y equals constant y x to the y. Why is this? Well, you see, 0 to the power of anything is still 0. So this can happen on the top, but not on the bottom. So we get this value out. Okay, that's pretty easy to understand. So you can imagine we sub a number in there. That number is in y. And this, of course, is based on the property we all know, a over b to the to the c equals ac over bc. Pretty simple. Probably learned this in calculus, pre-cal. Okay. So now we get to do roots, square roots. This will be fun. Oh, you probably actually want me to do the this property here. Okay, we can do that. So here's what we're going to do. We're going to say, we're going to go a bit, I almost want to do roots first because I feel like they tie in. Yeah, we're going to do roots first. So we're going to have the root of y, the yth root of x over 0, like so. This is going to be equal to the yth root of x divided by the yth root of 0, like so, which equals, of course, as we all know, c y root x. So it's pretty, because any root of 0 is still 0, like so. Okay, so with that done, we get to move on to the next the next number, which is as follows. So we'll do the property first. A to the b over c equals the root of c with a times b inside. Because what are roots? Really, they're just fractional components of exponents. They can all be translated back into this. Okay, so now we get to plug something in. So we're going to do the reverse of this, because we've done, roots are basically the same thing. That's just what I'm trying to get at here. A to the x over 0 equals the 0th root of a to the x, which in turn equals a to the power of x to the 1 over 0. This is the same. This is literally the same thing. Which in turn equals a to the power of c times x. Because if you think about it, if you have an exponent and you exponent it, you just take the top, merge them, and you get that value right back out. So you get this. So this is as far as we can go. We cannot break this down further. So yeah, this is another interesting result, because now we've retained our number below, and now it's got a power of this, and it's basically impossible for us to break this down any further in variable format. So we've got a bit of an oddity here. So now you may be wondering, what's the result of x to the power, or x over 0, I should say, to y over 0? Well, you got to understand, this is it gets weirder still. Root, 0th root, x y over 0y, 0 to the power of y, like so. And this, of course, equals the 0th root of y to the x, or x to the y over 0, which in turn gets us right back out c x to the power of c y. So powers are a bit of an outlier, because we cannot get a value out of them that condenses down to a c format or a full number like we had with this division here. We are left with a number that is not particularly satisfactory. Now, there are ways we can complicate this further, but we won't be getting into those too much. Whew, we've done a lot. So now we get to break this down even further with more complicated shenanigans.